Welcome. In this video series, we are covering how to build a bunch of different logic gates, and this video covers NOR and OR gate. You can find the playlist in the description. Okay, let's continue with NOR gate. As you can see, the symbol is like this, and yes, we are not using OR right now because it's like the NAND version. The OR needs one more transistor and it's more complicated, so I will cover that after NOR gate. And so OR gate symbol is like this, and when we put a bubble in the end, it inverts it and turns it into a NOR. Here you can see the Boolean representation, and here also you can make a NOR gate with an AND gate but inverting the outputs for people that want more advanced stuff. And just to cover something really small, when I say plus or multiplication, it's not like a normal math algebra, it's Boolean algebra. So 1 plus 1 is not like 2, it's just 1. So 1 plus 0 is 1, 1 plus 1 is still 1, 0 plus 0 is 0. Okay, let's look at the NOR gate. Let's power up the circuit and test it. Okay, let's read from the output, which would be right here. And we're reading 5 volts because both inputs are 0. So when we are giving 0 volts to both inputs, we are getting 5 volts. So it's a 1. And when it's one of them turns into a 1, either of the inputs are like 5 volts, one of them, we read 0 volts as 0 logic. Same situation for like this. As you can see, the voltage a tiny bit dropped because if both of the transistors are on, it's like a parallel resistors together, so the resistance gonna drop, and both of the inputs are 0. It's only that time gonna turn into a 1. And you can see the transistor configuration is in parallel, and so this is not much different than the NAND PNP version we saw, but the logic is kind of changed. It's because it's a different transistor type. And so you can see the common pattern right now. We had like in series with the NAND NPN version, and we had in parallel for the NAND PNP version. Then we have a parallel for the NOR version, NPN. And so you can probably guess the next one. Yeah, it's going to be a series PNP for the NOR. And let's try that in the circuit. Okay, let's read the output of the PNP, the NOR gate, it's right there. And when both inputs are 0, we are getting 5 volt. If either of them goes into a 1, you're going to see 0 volt. And I don't have to connect it because of the pull-up resistor, like I said. And if both of them are 1, same situation, just both of them are 0, you're going to read 5 volts. So it's a 1. So what is happening here? When we give 0 volts to both PNPs, both of them turns on, and so we allow the current flow, and the 5 volt here gets shorted to the output. So we read 5 volts. But if either of them are 5 volts, one of the inputs, then this one is, for example, off, but this one is shorted, this one is on, but it doesn't short to 5 volt because 5 volt stops here, it doesn't connect to there, and therefore we read 0 volts on the output. And for the NPN one, it's like the similar situation. If both of them are 0 volts, it stays off. Because for an NPN, we needed to give 5 volts to turn on the NPN. So if it's off, then the 5 volts here is seen on the output because the 0 volt is not shorted there. But if either of them gets 5 volt, the 0 volt here gets shorted there and we read 0 volts. Okay, then let's now talk about OR gate. Like in the AND gate, we just have to invert the output. Here you can see the bubble here is gone because it's not inverted anymore. And for making the OR gate with an AND gate, you have to invert 3 locations and you get an OR gate. Here are the Boolean representations. And I'm not going to cover the circuit anymore because it's just the same thing. Let's actually connect it and see. Okay, same situation. We are going to connect the input of the NOT gate to the output of the PNP. I mean the NPN, sorry. And let's turn on the power supply and read the output of the NOT gate. So if both of them are off, we read 0 volts. If one of them is 5 volts, we read 5 volts because we invert the logic. If both of them are 5 volts, we still read 5 volts. This one is 0 volt, we still read 5 volts. If both of them are 0 volts, then yeah, we read 0 volts. So this is a NOR gate being inverted and turned into an OR gate. Let's look at the PNP version. It's the same thing. We again have another inverter on the output. So we connect the NOT gate to the PNP version of the OR gate. Let's do that. And when both of them are 0 volts, we read 0 volts. If either one of them goes to 1, we read 5 volts. Both of them 5 volts, we still read 5 volts. If both of them 0, then we read 0 volts. Okay, that's great. I think we now understand this part. Okay, let's talk about a couple of special cases that you shouldn't probably do. So don't do this. So people looking at internet, you might see that some people make a OR gate with just connecting two inputs together like this. This is a bad idea. But you might wonder that, so it works. Why is it a bad idea? Because if you give 5 volts to either of them, it's going to turn it on. And we're going to see 0 volt here. So sorry, it's a NOR gate actually. But if you give 0 volts to both sides, then we're going to read the 5 volt from here. We are not shorting 0 volts to this location. This is bad because if you get 5 volt on the output right here and 0 volts here, you can see that the current gonna choose the low resistance path. So it's gonna choose going from this 5 volt down to this 0 volt right here and going to the ground. So most of the current is not going to pass through the 10K resistor, and the NPN is not going to get enough current, and this transistor going to partially turn on. So this is bad. And the second problem, you might actually fix this problem by connecting resistors with some other different values and different configurations. But the second big problem, let's say this location is not only connected to here, it's actually connected to some other logic. And so if you have 0 volt here and 5 volt here from the logics, this 5 volt here going to affect this logic right on the other side, which is why I think this is just a bad idea. You're just not making a stable thing, and it might work for just one OR gate. But if you're making multiple OR gates and making a big logic, which we are going to be doing soon, this is a not very good idea. It's going to mess up the whole big logic if you have many logic gates connected together. Moving on to the next problem. Also, you shouldn't be doing this. Can you see the problem? The resistor is on the emitter side. It's not on the collector side where we usually put the resistor for the NPN case. And it's the same situation for the PNP case. If for the PNP case, if you connect the load resistor up instead of down here on the collector side, you're going to encounter the same problem. But I'm just going to show it for the NPN case. And so let's actually see this with a simple circuit. Let's read our output right here from the NPN, which is shown in the circuit right here. As you remember, the output was usually here because the resistor was here, but it's now moved down here. If we now give 0 volts to this transistor, everything is okay, right? We are reading 0 volts, everything is perfect, working fine. But if we give 5 volts, see what happens. The output is reading 2.8 volts instead of something close to 5 volts. So this transistor is actually partially on. Let me actually show you with the both leads. Let's see the voltage across the resistor first of all. We have 2.8 volt across the resistor, and we have 2.1 volt across the transistor. Usually the value we saw was 0.02 volt across the transistor when it was on, but now it's 2.1 volt. So the resistance of the transistor is high, so it's not acting as a switch, it's acting more like a resistor, and so it's partially on. Then this is bad. You shouldn't be using a partially on transistor for logic gates. If you remember from the TTL logic, we should read from something above 2 volts to see it as a logic 1. And you might say, we read 2.8 volts, so that's a logic 1. Why is that a problem? Well, yes, but if you connect 2 or more transistors like this, the next transistor going to read 2.8 volt on the base. So 2.8 volt goes to the next base of the transistor, and that transistor is getting less voltage, and then that's gonna even partially turn on more. Like it's gonna have a high resistance, and that's gonna like drop a lot more. And then we won't see a logic 1. And in the previous video I showed why this was actually a bad idea, and this is actually used in analog circuits instead of digital circuits, which is what we are doing right now. So as like a brief explanation on what is going on here, actually let me remove this secondary part. I was kind of lazy to make another one next to this and show how that one is going to be not actually a logic one. But I don't think I need to show that because it's pretty clear if you're getting 2.8 volts here, this is just not good. And so what is happening is that this NPN was normally used to receiving 0 volts on the emitter side and some voltage on the collector side. So what happens is that in order to fully saturate the transistor, you have to give enough current to the NPN flowing through the base like this and to the emitter. And we have a 0.7 volt across this base to emitter because this is essentially acting like a diode. And when you don't have enough voltage difference from the emitter to base, there won't be enough current. Because imagine you have 5 volts here, right? But now 2.8 volts here. So, and you subtract 0.7 voltage drop across this transistor base to emitter. So you are reading essentially 2.1 volt here. And you can calculate the current passing through here. And this is going to be much lower than what we had before, which was 0 volt here, 0.7 volt drop. So it's 0.7 volt here. And we have 5 volt here. And you can see the difference, the voltage difference is much higher here, so much higher current is going to pass, but not in this case. So it's not going to fully turn on because not enough current is passing through the transistor. Those calculations are shown in the previous video. Thank you for watching. In the next video, we are going to cover XNOR and XOR gate. You can find the playlist in the description.